Before you can master physical geography or atmospheric climatology, you have to look up. You need a structural blueprint of our cosmic neighborhood. Our solar system isn't static. It is currently hurtling through the Orion arm of the Milky Way galaxy at over 500,000 miles per hour. This visualization shows the true scale of the Sun. It contains 99.8% of the system's mass, creating the gravitational anchor holding 8 planets in orbit. Its 15 million degree core is the energetic engine driving exact climate cycles on Earth. For an exam candidate trying to memorize discrete, random facts about 8 planets, hundreds of moons, and billions of debris fragments is highly inefficient. Instead, you use comparative planetology. By categorizing celestial bodies based on their structural differences, you can quickly deduce the answers to complex statement-based questions. To apply this framework, we start by splitting the solar system in half. The dividing line is the asteroid belt, a massive ring of rocky fragments orbiting between Mars and Jupiter. Everything inside this boundary makes up the inner or terrestrial planets: Mercury, Venus, Earth, and Mars. This 3D matrix reveals their shared profile: compact, highly dense, rocky, with almost no moons. Examiners test for anomalies here. Venus spins retrograde, clockwise, and features a runaway greenhouse effect from a dense carbon dioxide atmosphere. Mars presents a different anomaly. Its surface is heavily oxidized and rich in iron, giving it a barren, distinctly red appearance. These shared traits exist because the inner planets formed close to the Sun. The intense heat stripped away lighter gases, leaving only the heavy, rocky cores required to support eventual geological activity. Cross the asteroid belt, and the physical rules change entirely. Here you find the outer, or Jovian planets: Jupiter, Saturn, Uranus, and Neptune. This side-by-side comparison illustrates the extreme shift in scale. The Jovian planets possess massive volume, but much lower density, because they are composed almost entirely of hydrogen and helium gas. Their sheer size creates complex gravitational environments, allowing them to capture dozens of natural satellites, like Jupiter's Galilean moons, and maintain extensive ring systems. Beyond the major planets, we also categorize minor bodies. Asteroids are rocky remnants closer to the Sun, while comets are bodies of ice and dust originating from the freezing, distant reaches of the Kuiper Belt and the Oort cloud. And context matters. A rocky fragment drifting in the vacuum of space is a meteoroid. It only becomes a meteor when it strikes a planetary atmosphere and burns up. These massive gas giants and frozen minor bodies serve as deep space time capsules, preserving the original chemical building blocks that formed the early solar system, which brings us inward to the third planet. Out of all these varied bodies, why is Earth the only one capable of sustaining life? This map highlights the Goldilocks zone. Earth sits at the precise distance from the Sun where surface water remains in a liquid state. Add to that a protective atmosphere. The specific balance of nitrogen and oxygen physically burns up meteoroids and deflects harmful solar radiation. Even its shape is highly specific. Earth is not a perfect sphere. It's a geoid, slightly flattened at the poles and bulging at the equator due to its rotation. Habitability isn't random luck. It is a highly specific alignment of optimal distance, chemical atmospheric balance, and magnetic shielding. This physical framework is exactly what drives modern global space exploration. Take India's Mangalyaan, the Mars orbiter mission. ISRO scientists use comparative planetology to analyze these terrestrial surface anomalies directly against Earth's geology. Executing these deep space probes requires immense technological infrastructure. Launch vehicles have to generate massive thrust to break entirely free of Earth's gravitational pull, and we are pushing further out. By sending the New Horizons probe past Pluto and into the Kuiper Belt, researchers are actively mapping the entire hierarchical structure of the system. This structural logic, categorizing bodies by density, composition, and distance, provides the context for understanding why our own planet's geographical systems are unique. It is the first step in mapping humanity's future.